try to hit some other buttons here. You had a test, and there was only 5 of you in it. And 40 of you got 50%, and 1 of you got 100%. Do you know that the average for that class would be a lot higher than the typical person? And the reason for that is that one big number, like 100, will kill the thing off. An analogy might be, here's a pretend company, a very small company, but everybody gets paid $500 a week. So it has 3 workers and they all get paid 500. And then you've got 1 manager who gets paid $2,000 a week. It's a small shop, 3 guys work for him. He's the boss, he might even be the owner. If you're an owner, I guess you can pay yourself whatever you like as long as you have profits. If you found in this story the mean, which is very often written as an X with a little hat above it. So if you see that, it's the mean. You'd add up these things together and you get 3,500. You divide by 4. And I'm looking for my calculator. Which is not around. Well, what do you get? You get
875.
Thank you. 875. Now, legally, but not realistically, couldn't this guy advertise for a new position? Let's say that guy didn't like what he was getting paid and left. He legally could advertise or say, the average person in our little company gets paid $875 a week. That's really not a fair reflection of the typical person. If you were going to do, on the other hand, the median, well, you've got 4 numbers. And there's 2 on that side, 2 on that side. But this time the median doesn't have a problem because the 2 guys in the middle are the same guy. So the median is 500. Can you see in this story, it's much more realistic to say that the typical person in this company gets paid 500. So you would think that the median should get used in lots and lots of other circumstances. It's only used in one situation. It's used to represent the typical person in a group. But you'll find that as we go through this chapter, that the mean, with all its flaws and with all its faults, gets used more often because there are more things you can do to a mean. You'll find out later on that we can use it in things called normal distributions, and we can use it to predict what's the likelihood of a certain thing happening, and so on. And so the mean has its drawbacks, but we still use it. And I would think in this case, the median is a much better example of that. Now, let's look at some visuals. Right, imagine these are visuals of a histogram, right? It represents a large set of data. There. This picture here, as badly as it's drawn, is meant to be symmetrical. Roughly, anyway, right? Just like a single hill, equally spaced. When you have a picture like this, the top of the hill, the place here, whatever that number is, that's where the mean is. And that's also the same place where you'll find the median. That seems reasonable, right? So if your data is symmetrical, right, you can cut it into 2 equal halves and they're both basically the same. You would expect in those situations that the mean and median are pretty much the same as each other. Which means it doesn't really matter which one you use because they're both going to come up with the same number, or give or take a little bit, pretty much the same number. Now this second picture Can you remember what name you gave to data that looks like that?
The right slant.
The right is good. Slant's not a term I would use.
Right skewed.
That's
skewed,
the one.
That's it.
Yeah.
Thank you. That's the one. Skewed. Right skewed.
It's just jargon, but we try to use the right stuff. So it's right skewed. You could also say skewed to the right. Now, in this case here, right, in this world here, and you were looking at where would the mean and where would the median be. The median typically is either where the hill is or darn close to the top of the hill, right? Not far away from it. That's where the median will still be. Where do you think the mean is going to end up? Do you think it's going to be to the right of the median or to the left?
Be to the right.
Yeah. I'm not saying this is exact, but it'll be about there. But if you're not thinking why that's the case, can you see all these big numbers here? Aren't they going to be like 2 or 3 people in your class who, got 100 out of 100, and that's why the class average is so high, right? They're pushing it to the right. And have you noticed that the mean gets pulled to the direction of where the big numbers are, or at least the outliers are, right? So it would happen here. Now, this one below it has a similar name to the right skewed, but this one's called left skewed. And when you do a left skew, the median is somewhere either at the top of the hill or down close again. But there is a change now. Where do you think the mean is going to end up in distributions that have this shape? To the left of it or to the right?
To the left. To
the left.
Yeah.
Just guesstimate somewhere about there. So if I see a picture of data, I can tell you just by looking at the shape whether the mean and median are probably going to be near enough the same number, whether the mean is going to be bigger than the median, or whether the mean is going to be less than the median. Are we good? Right. So let me see if I can now share a different screen. Right. Again, as usual, are you seeing a screen with some rectangles on it and some pictures, and it says in class notes? Okay, so yeah, okay, so here goes. Some funny notation. We've talked about the mean. There it is there. Maybe make this a little bit bigger. Do one page at a time. There we go. That funny symbol there that's next to the X is called sigma X. It just means you add up all the numbers, all the X's, and you divide it by N. So that's, I think you'll see that in the textbook somewhere and you wonder, what's this? It just means X bar, the mean, is add up all the X's, add up all the numbers, and divide by N, the total amount of numbers there are. And the median is the data. So here is an example of a set of data. What's that? 2, 4, 6, 8, 10, 12, 14, 16. Okay, it looks like there's 17 numbers here. If you went and said to me, what's the mean of those 17? I'm going to go to that TI-84 thing that I showed you earlier and just plug that in, because I know how careless I am when I do boring things. And to me, adding up big lists of numbers is boring. So I would do it that way. But you could certainly just go 1, add 2 until you finished. Make sure you get the total and then divide by 17 in this case. But suppose I want to find the median since it's here. The data is in order. So if there's 17 numbers, where's the middle one? Well, if I call this guy number 1, 2, 3, 4, 5, 6, 7, 8, 9, this guy here is the median. 17 numbers, but guy 9. Now try and figure out why that happens. If you take 17 and you break it into 2 parts, you don't get a whole number. you get 18 and a half. And there isn't an 18 and a half person, right? Or 8 and a half person. So if the data is odd, like 17, add 1, 18, divide it by 2 is 9, and that tells you to pick out guy number 9. Right? So if there was 11 numbers, add 1's 12, divide by 2 is 6. Guy number 6. Now the thing is, you can check this. If you count in from this side, this is guy 8. From this side, 1, 2, 3, 4, 5, 6. Did I count these? 2, 4, 6, 8, 2, 4, 6, 8, 9. 2, 3, 4, 5, 6, 7. There we go. 8. 1, 2, 3, 4, 5, 6, 7. So there's number 9. Finally counted it. I've not got great eyesight. Here we go. It's 1, 2, 3, 4, 5, 6, 7, 8, 9. There he is. 1, 2, 3, 4, 5, 6, 7, 8, 9. You see he meets in the middle. That is your median. Now, what does that look like visually? Well, here are some examples. Here are some ACT scores of a large number of students. That little triangle is where the mean would be. You see it's roughly in the middle. The reason it's not exactly on the 24 is that this shape isn't quite balanced. Do you see there's a few more on this side than there is on that side? So that shifted it a little bit, but not much away from the middle. Right? Now, it's almost impossible to tell you why that's the right answer, but trust me, that's where the mean is. And you might see, well, God, there's a ton of numbers here, really tall, and then it drifts away. Well, do you see all these little 1s and 2s that belong all the way to here? Especially that little blighter at the end. Do you know that little blighter adds a lot to the mean and it shifts it to the right? See if I took care of, I don't know, see if I took care of a big chunk of data, you know, say from here to here, and I just pretended that it was gone. This thing would start moving more to this side because of that. So one big outlier can really spoil your day. Now, here is a histogram, and it says estimate the median and estimate the mode. So I'm not going to do it by calculation. I'm going to do it as a kind of guesstimate, right? Now, I see the shape, and it is pretty clearly skewed to the left. Great. If I'm going to pick the median, don't you pick pretty close to the center? So I'm going to pick it around about 40. But I'm going to make the mean a little bit more to the left. So I'm going to make the mean about 35. So my guess would be the mean is 35 and the median is probably 40, right? I'm at least making the mean more to the left than the median. Now, you can certainly argue about the number, but not the relationship that the mean is smaller than the median. This one's probably easier. Now, let's look at this shape. Would you agree that it's pretty symmetrical? So wouldn't the mean and median be pretty much the same number? Maybe a little bit out, but not enough to be a big deal. And would you agree that roughly about here where the mouse pointer is the middle? And in symmetric data, the middle is what, in this case, 3.5. So I would guess mean is 3.5, median is 3.5. Right, now this data here is very boring because almost every single one of them is the same height. Would you say that this is also symmetrical in shape, just a different kind of symmetry? So where's the middle this time? About here? 3.5. Mean 3.5, median 3.5. This shape here is a little bit less symmetrical. Roughly in the middle, it's about here. So very roughly about 3.5, maybe a little bit bigger. Would you think that if I say 3.5 is the median, right, in the middle, do you think the mean's going to be a little bit to the left or a little bit to the right? Right, you're pointing in a direction. What direction is that?
It looks like because it's got a left skew. So would it be more to the left, a slightly left askew?
Yeah, I'm trying to see that skewedness. I don't. It's
Yeah.
not dominant enough in my brain to say that it is, but that doesn't mean your choice is not a bad choice. It just means
Those were the challenging questions for me on the quiz, just to identify those differences subtly.
right. Yeah, and you know when it's one of those guesstimate questions. If I think it's 35 and then the back of the book or the solution sheet says it's 37, I'm not considering myself wrong. I'm just considering that I'm bad at guessing, because it's in the ballpark, right? It might not be exactly that fella. Right. So for the time that we've got left, let's look at a second summary of the data. And this is called the summary of the spread. And so this is a single number that kind of gives you an idea of how spread out the data is. And there are two, well, technically there are three versions. So I'll tell you what all three are, but only two of them are really useful. There's the range, which is pretty pointless, but we'll tell you anyway. And then we have got a guy called the standard deviation. And then we have a third guy called the interquartile range.
Oh, you still have the Word document up on if that's
no, you're right. Was not. Thanks for telling me. Here we go.
Yes, sir.
So we got a range, a standard deviation, and a thing called the interquartile range. Now the calculator is going to be your friend for the standard deviation and for the interquartile range. If you try to calculate, especially this one by hand, you don't want to. You can look up the book and see how you would do it by hand, but you really do need a calculator to do that, right? So let's give you an idea of some data and show you what it is. So 1, 4, 9, 17, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so here is 9 numbers in my data set. And I'm going to show you how to get the range, and then how to get the interquartile range. The range is easy. It's the biggest number, take away the smallest. Well, in this case, the biggest is 41, the smallest is 1, the range is 40. So it does give you an idea of how spread out the number is, right? From the oldest person in the class to the youngest person in the class, the range is 40, right? From the person who got the best score in the test or quiz to the worst scores, right, was 40, right? So it's a number, it does give you a kind of feel for it. So doing an analogy, suppose I had 2 statistics classes and I told you they got the same quiz, but class 1, the range was 80, and class 2, the range was 10. Well, in class 1, the range is 80. Doesn't that probably give you the impression that the scores were all over the board? I mean, from the best score to the worst score, there was an 80-point difference, right? So the person, somebody got 100 out of 100, right? And the guy at the other end got 19, right? Huge spread. And the second class, well, the spread was only 10. So if nothing else, doesn't that tell me that the second class were very consistent at what they got, right? From the best to the worst, there was only a range of 10 numbers. What the range doesn't tell me is how good they did. Couldn't you be a consistently bad class and everybody got 20-something in the test, right? That would be a very small range. Or a really good class and everybody got 90-something. Right? That'd be a very small range. Right? So the range does not give you any information about the typical person in the class. The range's job is how spread out the numbers are in that class. That makes sense? So they're measuring different things, right? One's measuring the typical score you would get in a test. The second one is measuring how spread out that number would be. Now, one of the biggest drawbacks with calculating it with the range is, isn't the range really susceptible to the biggest and smallest numbers? Because they're the only two that are used. And if either one of them was an outlier, you could get a really big range when in real life, most of the people were similar scores. So here's a different data set. There's 6 people. Excuse me. Come on, guys. Let's go. Right. Here's a very small data set, but it gets the idea across. Do you know the range of this is 80? But really, isn't the vast majority of the class got no range at all? They all got the same score. So what caused that huge number? One guy, the 90. Right, he's an outlier. He's clearly different than the rest of the group. That's why we don't use the range very much, because it is so susceptible to one number at the beginning or at the end being extreme compared to the rest of the data set. So what we're going to do is show you the second one. So I have my data set here, and we're going to find this weird thing called the interquartile range. Now, you can do this by hand. You can also do it with the calculator. Once I've shown you by hand, you're going to decide yourself whether you think you need it to do it for the calculator. But trust me, when you come to standard deviation, you have to do it with the calculator. So here goes. To get this weird thing called the interquartile range, you find a guy called Q3 and you subtract a guy called Q1. And you think, oh God, we've got some more guys to calculate. So here goes. 1, 2, 3, 4, 5, 6, 7, 8, 9. So guy in the middle is him, but he's called the median. Actually, he's also called Q2, that's his other name. So the first thing you do is you find the median of your data, right? The middle guy. Now, I want you to imagine there's a little invisible wall going right through here. And that invisible wall, in this particular case, kills the number 23. Do you see that I now have two separate sets of data? I have the small half of numbers, and I have the big half of numbers. Now look at the small half, these 4. We find the median of those, the middle of those. Right, since there's 4 numbers here, doesn't that mean that the middle is between 4 and 9? Right, there's only 4 numbers. Who's the middle? Those 2 guys are in the middle. So the guy that's called Q1 belongs here. And what's that, 13 halves? 6.5. And on this side here, 4 numbers. Can you see that the middle is those 2? And right in the middle here, you get 28.5. So Q3 is 28.5, Q1 is 6.5. Take that away from that, and you get 22. So this thing called the interquartile range is the number 22. Now, if you're wondering what does that 22 represent, can you imagine you've got all the data in a big row, and you took the middle half, right? The people in the middle half, right? The distance between the first and the last person in that middle half is 22. Now, why does that help? See that number at the end is 41. Do you know that could have been 4 million in one, and it wouldn't have changed my answer one bit, because it doesn't get affected by the outliers, because that number is just a position that never gets used. It's just one spot out of many. It's just a position. There's still going to be 9 numbers. The middle is still going to be there. And it doesn't matter if that number there is extremely small, it will also not affect the calculation for this fella called the interquartile range. So it's much better than the range. It doesn't care about the biggest and smallest. It kind of says, I'm more interested in the middle. How spread out are the middle group? Because that's a better reflection of how spread out the data is. Now, for our last few minutes, I'm going to attempt, I'll see if I get lucky, to show you how to do that. And again, I'll put this on a video, how to do that on the calculator. So I'm going to hit start again. Oh, first things first, are you actually seeing this thing? You are? Okay, good. So move this out of the way for a moment. Right, so you hit start, you pick edit, and you see it's still got the numbers from my previous situation, so just hit a whole load of deletes. I've also gotten some notes that I haven't turned into a PDF, the same instructions, so if you like to see them just physically written down, you can. Right, so I'm going to put in the numbers right now. So as quick as I can, it's going to go 1 and 4 and 9, 17, 23, 27, 28, 27, 28, 29, and finally 41. Now, although that may have taken me about a minute, can you imagine you've got 20 numbers and they're all jumbled up? If you want to find the mean or the median or anything, can you imagine how much more trouble it's going to be to rearrange them in order before you even do anything? I mean, just time consuming. This is in order, but it wouldn't matter if I typed them all jumbled up. The calculator doesn't care. It fixes it for me inside its memory, so I don't even see it happening. So once you've got your data in, you hit start, you move over to Calc 1 again, and we use choice number 1, very frequent choice. If you just hit a whole load of equals here we go. The mean is about 19.9. The standard deviation, which is something I haven't shown you how to calculate, and if you go and look at the notes, you'll see how horrendous it is. But the standard deviation is called SX. I wish it was called SD, it would be easier to find, but it's called SX. Standard deviation. Technically, it's a standard deviation of the sample. And that guy comes later, that's the standard deviation of the population. There are 9 numbers. The minimum is that guy. Can you remember Q1, 6.5? You see the median, 23. You see Q3. You see it's the same numbers I got without doing the arse. Now, all you need to do to get the interquartile range is take Q3 and subtract Q1. That's your job. You want the standard deviation, you just write this number down, 13.2. You're done. Okay. You have a question?
Yeah.
Yes.
Do you want us to round up?
Round
Down?
You round to the nearest number always. So a 13.42 is a 13.4, but a 13.47 is a 13.5. So you always round to the nearest 1 decimal place, 2 decimal places. A lot of the questions say to the whole number or to 2 decimal places. Whatever it's asking, you round off to the nearest insert accuracy here. Anything else? Raven, are we good?
Yeah, I'm good.
Okay. Any other questions before we call it a day? Right. If you want to find out what your grade is, you'll have to wait about another day, maybe a day and a half. But trust me, as soon as I know it, I will shoot you an email. And I think that's it for today, unless we have some other questions.
Well, I did. There was one other thing I wanted to ask you before we go was with the quiz. As I was going through the homework and whatnot, and when you had an opportunity to manipulate the data, it gave you choices between StatCrunch and Excel.
Yeah.
And I leaned towards StatCrunch, but it didn't appear. That didn't appear on any of the. That option didn't appear on any of the answers for the quiz. It was all Excel.
Yeah.
So I need to pay more attention to Excel. Is that the takeaway?
Well, you can do what I've just done on Excel. I'm just going to use the TI-84.
Well, not so much for this material, but it was just in reference to the other material that we had studied.
Yeah,
I
just
guess
use,
going forward.
Yeah, just use the Excel sheets for those things. Yeah.
Okay.
The StatCrunch is good, but then that means it's another thing you have to learn how to do. And I'm not sure that the learning curve in that is worth the reward.
No, I wasn't too savvy on either one actually, and then I had spent more time watching YouTube videos on StatCrunch and learning StatCrunch, and then we got to the exam and it's like, oh shit, it's all Excel, and I didn't spend any time doing Excel, so it was like, oh man. So.
Well, that's called Murphy's Law.
Yeah.
If it's anything to do with number crunching, which is what chapter 3 is going to be, a lot of, doing stuff to batches of numbers. I think the TI-84 does is just as good a job as Excel, and you don't need to learn it, because it might have seemed a bit awkward what I just did, but I mean, once you've done 2 or 3 questions, it'll be fine. Put in the data, read it off from, the list. Put in some more data, read it off from the list.
So the TI-84 would be something to have opened on the side as we're going through the next exams.
Yeah, it's a nice piece of software. As I say, you get a 90-day free trial, so you're good to go. You can stick it at the side. You can, bring it up when you need it. If you've got your own physical version, that's even less hassle. Okay, bye-bye, guys. I have to go.
Thank you. See you Friday.
Okay.